this talk, we will see how spectral information or Higgs kernel of a manifold can be used to capture the geometry of the manifold and how it can be used in data analysis, especially to deal with the cursive dimensionality problem. The main idea here is the Higgs kernel or spectral information captures geometric structures of manifolds. And we're going to see this from three perspectives. When we have a high-dimensional data set, it is very hard to see the structure and analyze the data. So what we need to do is to put the data into a lower dimensional structure without destroying the structure too much. So this is called the dimensionality reduction problem, and spectral geometry can help us partially solve this problem. We will also see an application in biological morphometrics, and you're gonna see how the Higgs kernel can help you to capture the geometry there. Last, we will see some theoretical results based on diffusion maps. Higgs kernel captures geometry. What does that mean? Let's say we have a compact manifold without boundary. To give you a concrete example, think about the surface of a donut or the surface of a basketball. So they are a surface and doesn't have a boundary. So this is a two-dimensional compact manifold without boundary. On this manifold, we can look at the Healy equation, that is ddtf equals Laplace f. And the fundamental solution of this equation has a name called the Higgs kernel. So when we say the Higgs kernel of a Healy equation, or the Higgs kernel of this Laplace Tramiel operator, we are talking about the fundamental solution of the Healy equation here. And it satisfies several properties. Let me just list two here. We know that on any surface, locally, it will look like a Euclidean space. So locally, the Higgs kernel solution actually looks like the Higgs kernel solution on Euclidean space. And we do know the Higgs kernel on Euclidean space exactly looks like this: 1 over 4 pi t whole thing to the power d over 2 times this exponential function. The d is the dimension of the manifold. Moreover, if you have two manifolds or two surfaces that have the same Higgs kernel, then this is equivalent to saying these two surfaces are isometric, meaning there is a map between these two manifolds that preserves the lengths and angles. On the manifold, let's take the same Laplace-Beltrami operator and we look for the eigenvalues and eigenfunctions. So the eigenfunctions we called phi L. The eigenvalues, that's called nu L. And you can see that the eigenvalues v0, v1, they keep increasing all the way to infinity. Sometimes we also call these eigenvalues frequencies. And the fundamental solution, Higgs kernel, has this series expansion expressed by the eigenvalues and eigenfunctions according to this equation. So it's the sum of e to the minus nu lt times phi L at x times phi L at y. Now let's take these eigenvalues and eigenfunctions, and we use this to define a map that is called a diffusion map at a diffusion time t, according to this psi t definition. So for each point x on the manifold M, we can put this point into a sequence space. So think this sequence space as a infinite dimensional Euclidean space. And the coordinate functions are defined by this: e to the minus nu lt over 2 times phi l at x. So this map is the so-called diffusion map. And it is worth to mention that if we define the diffusion map this way, then the heat kernel kxyt is actually equal to the inner product of the diffusion map at x and the diffusion map at y. So what you do is you compare the series expansion of the heat kernel at line 2, and you use the diffusion map at line 3 to do the dot product, and we will see that the heat kernel equals psi at x dot psi at y. The eigenvalues and eigenfunctions here are the so-called spectral information. And now you can see that heat kernel actually encodes spectral information. So sometimes I say heat kernel, sometimes I say spectral information, but in a sense they are more or less equivalent. We have discussed what spectral information and heat kernel are. So let's now move on to high dimensional data. What is high dimensional data? Let me give you an example. Here I have 15 images, and each image is of size 127 pixels by 169 pixels. And each pixel needs 3 numbers to describe the color densities of the red, the green, and the blue. That's the so-called RGB systems, right? So now for each image, I will need how many numbers to describe the image? That is 127 times 169 times 3. Therefore, if you think about this is a point in a Euclidean space, it's gonna be a point in the Euclidean space of dimension 127 times 169 times 3, and that's a pretty big number. And here we're talking about low resolution images, and each of these images are a point sitting a pretty high dimensional Euclidean space. So if you think about the images you have in your phone or on your computers, they are sitting in way much higher Euclidean dimensions. And this is the so-called high dimensional data. When I have a high dimensional data, you can think that they are points sitting in a very high dimensional Euclidean space. And because the dimensionality is so high, it is harder for us to find the structures and further analyze what we have from the data. So one thing that we need to do is to do dimensionality reduction. What does that mean? That means I want to put my data into a lower dimensional Euclidean space. It is not hard to construct a map that sends a high dimensional data point to a lower dimensional Euclidean space. Let me give an example. Those 15 images from the previous slides, we know that each image can be seen as a point in a high dimensional Euclidean space. And here is how I map these images into R1, the one-dimensional Euclidean space. I can say, okay, I want to send the first image into the point x equal to 1. Second image to be sent to x equal to 2. Third image to be 3. Fourth image to be sent to 4, and so on and so forth. So now what I have is 15 points, 1, 2, 3, 5, all the way to 15 are R1. But when I do this, what do I get from the data being sent to R1? I got pretty much nothing, right? Because I just construct the map without any logical reason. So when we construct a map per se to put a high dimensional data into a lower dimensional Euclidean space, we actually want this map to satisfy certain properties. For example, I want the dimension Q to be less than P, so then this is dimensionality reduction. I'm not mapping my high dimensional data into a even higher dimensional space. Second, I would like this map to be bi-Lipschitz, meaning the distance between points are not being distorted too much. And even better, I want this map to be close to isometry. And isometry is a map that preserves distance. So that means not only the distance doesn't get distorted too much, it would be even better if they're actually close. And I would also want this map to be robust to noise. So in real life, oftentimes the data you collect contains noise. So I want the map is robust to noise. Remember we talked about the diffusion map on a manifold. And from the theory, we can actually see that the phi0 is always a trivial eigenfunction. So if now I use the image data set that I have and compute eigenvalues and eigenfunctions, I'm gonna use phi1, the first non-trivial eigenfunction, and its associated eigenvalues, e to the minus nu1 t over 2. I'm going to use this coordinate to construct a map and send this high dimensional images to R1. And let's see what happens. So now I put each image into R1 according to the coordinate function e to the minus nu1 t over 2 times phi1. The t diffusion time is chosen by the user, so just any small number t would be fine. Okay, so if I list the images according to the points in R1, then you can see that this is the order of the images. And if you pay close attention, you can see that these images are being arranged and there's a structure among these images. You can see that the structure is a S1 structure, a circle. And you can see that from the first image to the last image, it is basically the toy truck facing the right, and it rotates until it faces the left. So it is an S1 structure. This is an example of how using the spectral information can help us to analyze the data and reorganize the data. Here is another example in biology. We have a collection of digital teeth from lemurs. What we want to do is to want to measure similarity of the shapes, so we can talk about the species of these lemurs and want to develop a model for the shapes. Okay, so the idea here is again to use the heat kernel to capture the geometry of the surfaces. The typical way to measure similarities between shapes is the so-called procrusted distance. Here we have two simple teeth. On each tooth, we have hand-picked chosen landmarks by biologists, and we have a correspondence between the landmarks. So I color coded the correspondence. The Let's say X1 is the orange on the left, Y1 is the orange on the right. So I know X1 corresponds to Y1 and X2 corresponds to Y2, and the correspondence is shown by the color. Now we fix the points yi's at R3, and we apply Euclidean translation onto xi's. So what I'm doing here is to find the best alignments between the points xi and the points yi. And now after I find the best alignment, then I measure the distance between each corresponding pairs, and that number will give me the procrusted distance between the surface M and the surface N here. Now use the idea that the heat kernel could capture the geometry of the surface, and we know that locally the heat kernel looks like the Euclidean heat kernel, which we have the exact solution. And because the surface is of dimension 2, therefore they have the same coefficient, 1 over 4 pi t. Let's just ignore the coefficient and focus on the exponential function part. So now I'm going to use the hand-chosen landmarks from the data and construct a matrix to represent each surface. So this is how I use the xi's to represent surface M, and how I use yi's to represent surface N. And let's see what would happen. Let's construct a synthetic data to see whether the matrix representation does give us a better representation, meaning whether the heat kernel idea does capture more geometry of the shapes. So here I construct 80 shapes into clusters. So 40 similar shapes and another 40 similar shapes. Okay? But even within each cluster, there's still dissimilarity. So let me give you an example. Shape 15, 30, and 35, they are in the same cluster, so they are very similar. But still, you can see that 15 is less similar than 30 and 35. But shape 30 and shape 35 are more similar. Okay? So each shape can be represented by a matrix that we discussed before. And the distance between two shapes, shape I and shape J, is the distance between the matrix from shape I and the matrix from shape J. So the distance will give me a number, and let's call this number dij. And because I have 80 shapes, so I'm gonna have a 80 by 80 distance matrix. So the item dij would be the distance between shape I and shape J, like this. Okay? So I have two distance matrices. One is the matrix that I get from computing procrusted distance between shapes, and the other is the matrix that I get from using the new distance, or the matrix representation. Because it is hard to look at 80 by 80 matrices, therefore I color code the numbers for you. Going from deep blue to light yellow is the number 0 to larger numbers. So you can see that along the diagonals, you should see deep blue, because that's the distance between a shape and the shape itself, right? So distance should be 0. Okay? So we can see that we do have two clusters. So the first 40 shapes, they are all in deep blue or purple. I cannot really tell. Um, so you can see the distance among these clusters are all small. But you can see that the new representation does give us a more subtle result because among each clusters, it can tell you that, oh, there is still some shapes are more dissimilar to the others. So this is an example showing that the heat kernel idea does work in the sense that it gives us more subtle details among the shapes. I hope from the previous two examples you you get a taste of how spectral informations and the heat kernel would help us to analyze data. Sometimes the data itself has a geometric structure. Sometimes the data contains rich geometry in that. So depends on what your data type is, you can have different use of spectral information and and heat kernels. So I want to talk about some theoretical results we have for diffusion map. So it is proven that under certain geometric conditions, the diffusion map can reach bi-Lipschitz and can even be close to isometry. And this is actually also robust to noise, but it does not always give us dimensionality reduction, meaning the Q is not always less than P if you want the map to be, let's say, close to isometry. Okay? What I want to do is to explore how much the spectral information can help us in biomorphometrics and dimensionality reduction.